Introduction with me. My name is Wissing, and I'm a student at SPCC, but in the fall I'm going to be transferring to UCLA, and I'm studying electrical engineering. So, like she said, over the summer I worked on a very interesting project under John Powers and Akhilesh Koch, my mentor, on contradirectional couplers for wavelength selective switches. So, the big idea of why this type of research is very important is because we can reduce energy consumption in data centers. And so switch is an important interconnect that's used in data centers that's really responsible for transferring our information and directing signals to where they need to go. And so data centers currently tend to use electronic switching, which is very affordable because there's a lot of infrastructure for manufacturing these components. But they aren't as energy efficient as they could be. So that's where optical switches come in. This is the big focus of research in our group. And an optical switch basically redirects light signals to the appropriate output and sends them where they need to go. And they are much more energy efficient than electronic switches because you never have to convert the light signal to an electronic signal, where most of the energy is lost. And so there is an issue with the cost of optical switching, but this is something that we could work to alleviate, and that's with wavelength selective switches. So this is a type of optical switch that was a big focus of my research. And so basically the nuance here is that you can have a fiber with light signals of many different wavelengths in one fiber. And you can use a wavelength selective switch with filters to separate the signals by their correct outputs. And so this overall is very flexible, and it also is cost effective because instead of having to lay down, say, 10 different fibers to get 10 different wavelengths, you can have all your wavelengths of light in one fiber. So that's a wavelength selective switch, and of course a very critical component to something like this is that you have to have filters. Later on in this talk, or this symposium, you're going to hear about different types of filters like microring resonators, but I worked on contradirectional couplers. And so it's very useful to have different types of filters because then you'll be able to cascade different devices together and overall make something that is just much more effective and more sophisticated than, say, one simple device on its own. And so to break down what a contradirectional coupler is, it's a device that consists of two waveguides that are basically connected. And so the contradirectional is referring to how light is traveling in one direction in a waveguide, but then travels in the other direction in the other waveguide. And so coupling refers to how light is being exchanged between the two waveguides, and the medium that we basically use to do this is a grating. This is a periodic structure, and the material and dimensions of the grating are designed in a very specific way so that some wavelengths of light are reflected, but most of the others will transmit through over to what we call the through port. And so that's the contradirectional coupler. I'm now going to talk a little bit about basically what the overall goals of my research this summer were. So what I wanted to do is examine how contradirectional couplers with various physical parameters would have different wavelength spectrums. So the way I started off by doing this was with some computer simulations. Basically, I read a lot of literature and textbooks about how these things work, and then from this knowledge, I was able to start constructing plots using Python that basically describe their behavior as far as efficiency goes and wavelength spectrums. And then another very important aspect of my internship was optical testing, where I would basically test the contradirectional couplers on a chip that some grad students on the team I was working under designed. So it contains a lot of test structures, and my job is to measure them. And the overall question I was examining is, how does the physical parameters such as grating length affect the wavelength spectrum? So this is my setup for testing the filters. What you're seeing here is basically the waveguides and the ports that go into the grating, which isn't pictured. But it's very small and hard to discern from a picture like this. And the overall methodology I was using is taking an infrared laser of varied wavelength. So I would change the wavelength in small steps and then see what type of optical power response I get, and construct plots using this. And so here's an overview of the methodology I did with the simulations, where basically the overall idea is that I have some physical parameters, coupling constant, which is dependent on dimension of material, and also the grading length, which is the main focus of my research. And so I plotted different values for different physical parameters, and basically observed how the spectrum changes a little bit. It might not look like there's a spectrum, but this is just a very generalized plot. Contains a factor describing phase matching, which depends on material, which affects the indices of refraction, describing how light propagates through the medium, and also lambda naught is basically any wavelength that would generate our operating peak. And then as you start moving away from that wavelength, you start to see changes. So here's some more results from my simulations. So basically I plotted reflectance, which describes how that peak wavelength would usually get reflected and then in practice sent to the drop port. And once again, I plotted different contributional couplers with different parameters. And then the transmission spectrum describes all the other wavelengths that go through and have higher power, except for the ones that get filtered out. So that's what I found out from my simulations. You can compare the results with my actual measurements. So, so this is what I measured in the lab. You can see how the behavior is fairly similar to the simulations, although I did find out that I would probably want to design a more sophisticated simulation to give a closer fit to the actual configurational couplers that we have on our test structures. And so one observation I had was that putting more spacing between the gratings overall shifted the peak a little bit to the right, such as you see here. The green one's the longest, it's farthest to the right. Normally we would probably want to have a peak wavelength around 1550 because that's the most important and most widely used range of wavelengths in the C-band for fiber optics communications. What we see here, the peak looks more like it's 1530, so if I were to personally redesign this, I would probably use longer spacing. And then some other observations I noticed from my data, there looks like there's a lot of inter-waveguide reflections. That's this oscillatory behavior.